Hello there. Can you hear me? That's brilliant. Let's start with the topic then. Oh, wait. You can't see me? Well, how about now? Well, I'm guessing you don't think it's a good idea to discuss a science chapter with a floating head, do you? Hold on for a while. Just a second more. This is a lot more interesting than a floating head, isn't it? A flying man. Are you wondering how I am making all this magic happen? Well, it's nothing but the magic of light. Hi there. So what's up? How is everything? Wait, are you laughing at me? Why are you laughing? Oh, that's just a magnifying glass. Well, I don't blame you for laughing. I'm sure that was looking funny. Have you seen a magnifying glass though? Actually, have you touched a magnifying glass? If you have, then I'm sure you know that it doesn't have a plain surface. Instead, its surface is kind of bulging outwards, isn't it? There is a specific name for glasses that have a curved surface, and they are called… Wait, are you laughing yet again? Why are you laughing this time? Oh dear, I really need to get this lens out of my way. And that's exactly what they are called. Lenses. That's right. A glass that has one or both of its surfaces as curved outwards or inwards is known as a lens. So far, you have laughed at two of my faces that were distorted by lenses. In the first one, if you observe, my features looked bigger than they really are. And that was achieved using a lens that was bulging outwards, which is known as a convex lens. The second, you must have seen that my features looked smaller than usual, which was achieved using a lens that curves inwards and is known as a concave lens. Now let's study more about these lenses and see why they distorted my lovely face like that. Before that, let's do a quick recap of the definition of a lens. According to the definition, a transparent material bound by two surfaces of which one or both surfaces are spherical forms a lens. So let's try different combinations of these surfaces and see the kind of lens that we get. But remember one thing, whenever the surface bulges outwards, it's convex, and whenever it curves inwards, it's concave. Let's say we have one plane surface and the other surface bulging outwards. This type of lens is known as a plano-convex lens. At the same time, if we have both the surfaces bulging outwards, the lens is known as a double convex lens, or simply convex lens. Next, if we have one surface as plane and the other curving inwards, then the lens would be a plano-concave lens. And when both the surfaces are curving inwards, the lens would be a double concave lens, or simply a concave lens. We are going to be studying how refraction occurs in the double convex and double concave lenses. So we'll only refer to them as convex and concave lenses respectively. Okay? Great. Let's consider the convex lens first. We can actually visualize the convex lens to be formed by the parts of two spheres, like this. So there are two centers of curvature of one convex lens, and these two are represented by C1 and C2, as you can see here. But the lens also has an optical center which lies in the middle of it. It is denoted by the letter O, and the special property of the optical center is that any ray of light passing through it will not undergo deviation and will travel in a straight line through it. Then we have the principal axis of the lens. which passes through both C1 and C2 as well as the optical center of the lens. The principal axis is also perpendicular to both the faces of the lens at the points where it intersects them. Next, a convex lens is also known as a diverging lens. Can you guess why? That's because it diverges the rays that pass through it. Let's say we have a beam of light passing through the lens, where the beam of light has light rays that are parallel to each other and are also parallel to the principal axis. When all these rays pass through the lens, they undergo refraction, that is governed by the laws of refraction, and they bend towards each other. Finally, they all converge and meet at the same point on the other side of the lens. This point where all the rays meet after refraction lies on the principal axis of the lens and is known as the principal focus, denoted by the letter F. At the same time, if we had instead made the beam of light fall on the right face of the lens, then the rays would have converged to a point on the left side of the lens, which also lies on the principal axis. Even this point is known as the principal focus. This means that the lens has two foci, which are at equal distances from the optical center, and they are denoted by F1 and F2. And the distances OF1 and OF2, which are equal to each other, form the focal length of the lens, denoted by the small letter f. Therefore, by definition, the focal length of a lens is the distance between the optical center and the principal focus of the lens. Also, the focal length of a lens is half of the radius of the curvature of the lens. Therefore, if r is the radius of the curvature, we get r is equal to twice of f or 2f. Do you remember that one experiment we did with the concave mirror and the sun? Yes, the one where we obtained the image of the sun at the focus of the mirror and ended up burning a hole in the paper. So let's do that again, except this time we'll use a magnifying lens, which is a convex lens instead of a concave mirror. So we'll take a sheet of paper and hold it below the magnifying lens. Then we'll go out in the sun and try to focus the sun's rays on a single bright spot on the paper by moving the paper back and forth. Now, since we have already done a similar experiment, can you tell me what happens if we keep the paper in that position for a long time? That's right. We will see a hole being burnt at the point where we had obtained the image of the sun. Again, this can be a dangerous experiment, so make sure you are very careful doing it and that you preferably have one of your parents with you.